Welcome to the presentation of Team 3, Denoised Smoothing as an Adversarial Defense for ASR. ASR maps an input waveform to their corresponding character sequence. That is, given some audio, we get the expected transcript. For example,
without the dataset, the article is useless.
This audio when passed would give us the transcript. Without the dataset, the article is useless. However, ASR systems are vulnerable to adversarial attacks, wherein some perturbation to the input, which we might not hear, can indeed have a large impact on the model output. For example,
without the dataset, the article is useless.
Though this seems fine, actually when you pass it through an ASR, we get okay Google browse to evil.com, which is a malicious transcript. How do we tackle these problems? One proposed method is randomized smoothing, wherein you add random Gaussian noise to the audio signal so that this sort of masks the effect of the attack, and this is a defense that against adversarial attacks. However, this can result in a degradation of ASR performance. In this project, we explore the avenue of using denoising diffusion probabilistic models that are generative models that successively add Gaussian noise to training data and learn to recover the original input by reversing the process, which is similar to what we are doing. That is, under attack, there is some noise that gets added, and we're going to be using the DDPM to recover the original input by reversing the process. So we will be conducting experiments using the LibriSpeech dataset, using pre-trained off-the-shelf models, and we will be applying targeted and untargeted attacks using the robust speech framework with the word error rate as our evaluation metric.
So coming to the approach. So generally the audio is passed to the ASR system and we get a transcript. With the perturbed signal, we get a malicious transcript. And randomized smoothing is when you add Gaussian white noise to get a smooth signal, but the transcript that you get is really noisy, even though you get good defense. What we propose is we pass the smooth signal to the DDPM. This will denoise it and then pass it to the ASR system, would give us a much better transcript. So the approach is to train diffwave, which is the DDPM model we choose, for unconditional wave generation on the LibriSpeech dataset. We do unconditional because we are in the waveform domain and the attacks are also in the waveform domain. We calculate the optimal time step T star to start the denoising process because we are not dealing with pure noise. We're dealing with a smooth waveform. So we calculate the optimal time step to start using sigma star is 1 minus alpha t by alpha t, where alpha t is the noise schedule that is used by the DDPM. And now the DDPM knows what level to denoise it from, and we experiment this with varying levels of randomized smoothing with sigma 0 to 0.04. We also use the Wiener filter, which is a statistical filter used in signal processing, which generally is used to remove noise, and we perform ablation studies with it. So in this table, we report results for the PGD attack, which is an untargeted attack, which is one of the attacks that we'll explore. And the first to show the effect of smoothing, we see that without smoothing, which is when sigma is 0, there is a big difference between the columns WER and ADVWR. WER is basically the word error rate without the attack, and ADVWR is the word error rate with the attack. So when you see a huge difference, this means that the PGD attack was very successful when applied. It gave the ASR system to output a transcript that's completely different from what it was supposed to have outputted. When we add smoothing though, for sigma 0.02 and 0.04, you see that the difference between WER and ADVWR has significantly reduced. It's almost non-significant. However, the magnitude itself is in 15 and 42 as opposed to 3.96. It significantly deteriorated the ASR performance, which is a problem with smoothing. What we do is we are past the smooth waveform for DDPM, and now we see that DDPM has actually helped quite a lot. In 0.02, it's reduced the WER from 15 and 16 to 12 and 13 respectively, and for 0.04, it's significantly reduced it from 42 to 13. So the DDPM is able to denoise the smooth waveform, and therefore the ASR is able to perform better transcription. We see that smoothing to DDPM to the Wiener filter actually works as the best. This gives really good defense because the difference between WER and ADVWR is very less, and at the same time the WER's magnitude are very low. So the ASR system is able to output really good transcripts as well. This is an example that we had. So for an original waveform of
"It is a very fine old place of red brick,"
and after we add randomized smoothing,
"It is a very fine old place of red brick,"
you can hear a lot of noise, and then we pass this to the DDPM.
"It is a very fine old place of red brick."
It removes most of the noise.
"It is a very fine old place of red,"
and the Wiener removes the remaining noise and just amplifies it. So to conclude, ASR systems are vulnerable to adversarial attacks. Randomized smoothing is effective, but it significantly affects the performance. Denoised smoothing is a good thing, and we can use DDPM, and DDPM combined with Wiener filter provides good robustness and even better ASR performance. Thank you.